We're going to start this video off regarding Newton's first law with actually just a demonstration first. So we're going to watch this car from two different scenarios. The first scenario is where we pull it with low enough force that the car stays on the paper. And the second scenario is where we pull it with more force that the car can't stay on the paper and it falls. We're going to explain what's happening with that real quick. So let's talk a little bit about what's going on in that car example. When I apply a force to the car in the first scenario, the force I'm applying to the car is not quite enough to get it to slide off the paper. Why? There's friction between the tires, the wheels, and the paper, keeping it on the paper. So let's talk about the first motion there, when the car stayed on the paper. Why did it stay on the paper? There was enough frictional force between the tires and the paper to keep the car from sliding off the paper, meaning I didn't pull it with enough force to make it slip off. And in the second case, why does it fall? Well, I pull it with enough force that the friction can no longer keep it from sliding off the paper. Once it gets off the paper, gravity is able to just pull it right down into the glass. This is Newton's first law of motion. So in 1687, he published his the Mathematical Principles of Natural Philosophy, where he actually has all three of his laws of motion published there. The first one has to deal with objects that have mass, and objects that have mass have what he calls inertia. What this means is if an object is at rest, it's going to stay that way. If an object is moving, it's going to stay that way unless I put an outside force on it. Now, the case of the object at rest, it's going to stay at rest. That is the thing that makes the most sense to us from what we can see in terms of classical mechanics. That's objects on Earth that we're most familiar with. The idea that an object in motion will stay in motion doesn't actually make a whole lot of sense to us, unless we consider that most of the motion that we're talking about is motion that happens in terms of the universe as whole, happens in space. Objects in space encounter very little resistance. In most cases, there's not hardly any friction or any air drag. There's no atmosphere for them to follow through. So there's no outside force that's going to get them to stop. Why do objects in real life stop if I push? So if I were to push the car across the floor, why would it end up stopping? Friction. Friction slows it down between the tires and the floor, and actually the tires and their independent axis of rotation. But in general, if I look at the normal motion of the universe, that Newton's law is true. It holds through. An object that is traveling at a constant speed is going to stay traveling that way. I can think of if I pushed an astronaut in outer space, they just continue traveling along at that same distance. And we can represent this with what we call free body diagrams. So free body diagram, because us physicists are the best artistes, we can represent, so let's go back to the car example. Before I've done anything to it, just while it's sitting on the paper and it's on top of the glass, I'm going to represent the car as the dot right here because I'm super good at drawing cars. And it has a force that's pulling down on it. Why does it have a force that's pulling down on it? Well, it's on Earth. There's a thing called gravity. Because Earth has a mass, the car has a mass. There's more details to it, which we won't get into in this video. But it has gravity that's pulling down on it because Earth is big. And we use subscripts to write that. So big F for this is a force. This is a vector, meaning it has direction and a magnitude associated with it. And I'm going to have a little subscript G here to denote this is the force from gravity. And it has another force, right? It's not falling through the paper. It's not jumping off the paper. It has another force that's counteracting gravity, which we call, essentially, this force from the paper is what we call the normal force, Fn, meaning the normal force that's perpendicular to whatever horizontal distance I'm on. In this case, the paper is completely flat. The normal force is pointing straight up. And this should be the same in magnitude. The normal force should be just as long as the gravitational force. Why? Because I can consider their net forces, and I treat this just like vector addition. If I add these vectors together, that I should get 0. My net force or outside force is 0, meaning this object's just going to stay there. That's what Newton's first law tells us. It's not going to move. If I consider the case where I am pulling with the slow, light amount of force and the car stays on the paper, I have gravity still pulling this thing down. It still has gravity acting on it. The normal force from the paper is still counteracting gravity. I've now introduced 2 additional forces, though. The force I'm using to apply it to pull it off the paper, which I can call F(a) for applied force. I'm just applying a force to it. And the force that's keeping it on the paper, the friction between the wheels and the paper. And on the first case where I didn't pull hard enough, it stayed on the paper. So those, if I do vector addition, take one and subtract the other, those should also equal 0 because it's staying on the paper. It wants to stay where it's at. Again, Newton's first law saying it's just going to kind of keep doing what it's doing. If, however, I pull with enough force, so it's still, gravity's still pulling down on it. The paper's still holding it up. And this time I pull with more force. I increase the applied force of which I'm pulling. My friction force is only so high. It can't grow like that. It's only going to be so much. If I then do the difference between these 2 vectors, I see that I have some net force in the positive direction, or we can consider this the right side of it. I have some positive force on that right side there. That force means I'm going to apply rotation. We won't get into all the specific mechanics of how the wheel will rotate, but essentially it's going to cause the wheels to rotate and the car to slide backwards. As the car slides off the paper, I lose the normal force of the paper. So that's another point of motion. Once it leaves the paper, well, gravity's still acting on it. It's still on Earth. Gravity's still pulling it down, but I now have no normal force pushing it back up. I also now have no applied force because it's not in contact with the paper anymore. I'm not touching the car, I'm touching the paper. And if it's not on the paper, there's no frictional force. It actually only has gravity once it leaves the paper, which is why it falls down into the cup.